Hi, today I want to talk about the ESP32 and a MOSFET to switch some load and what you have to consider if you want to use a MOSFET as a switch. A MOSFET or a metal oxide semiconductor field effect transistor, there are mainly two different types, a depletion mode that's normally on or an enhancement mode that is normally off. And we switch the MOSFET with an voltage and not with an current like an bipolar junction transistor or BJT. And today I want to talk just about the enhancement mode and using the MOSFET as a switch and just below in frequency about 1 kilohertz. And we talk about this later. And I've divided this in 3 parts. A small switch with a voltage just about the level of our GPIO pins from the ESP32 and just a little small current. Then we can go up to a medium range where you are about switching amps, and a medium power range where you switch in higher current and also higher voltages. And not covered in this series. If you need higher voltages about the mains level or even higher currents in the 10 amps range, that's not covered here. If we look at some MOSFET datasheets, we can see there's many parameters and many things to consider about using a MOSFET. Or if we see this example, there are other parameters, so we have to compare the different MOSFETs if we use one. So I focus on some main parameters for me: the continuous drain current, the gate threshold voltage, the gate source voltage, the drain source voltage, and also the drain source on resistance. And for thermal considerations, I also use the power dissipation and the R theta or junction to ambient thermal resistance. And in the enhancement mode, we have two main types of MOSFETs. The Nchannel MOSFET with a positive gate threshold voltage and a relative low on resistance. And in the schematic, the arrow is pointing towards the gate, and we have an intrinsic body diode where the cathode is connected to the drain of the MOSFET. And we have also the P-channel MOSFET with a negative gate threshold voltage, and in the schematic the arrow is pointing from the gate, and the intrinsic body diode, the cathode, is connected to the source of the MOSFET. And now we can compare the both types of MOSFETs. As you see, the arrow is pointing in the other direction from the N channel and the P channel. And because of the intrinsic body diode, mostly we connect the drain of the N channel MOSFET to the positive rail. And for the P channel MOSFET, we use the source to the positive rail. Because if you do it in a reverse direction, the current is directly flow through the intrinsic body diode, and so the current is flow also if we don't use any gate threshold voltage, and this is not so useful if we use the P-channel MOSFET as a switch. Now a practical example with an N-channel MOSFET. We have connected the source of the MOSFET to the ground level, the drain to the load. The load is also connected to the 3.3 volt rail, and we have our GPIO pin connected to the gate. And now if we have our GPIO pin to the low level or 0 volt or switch to ground, the MOSFET is off. And if we switch the GPIO pin to high or 3.3 volt, then the MOSFET switches on and the current can flow through the load, and an even higher current than is able to handled by the GPIO pin. And if we use the N-channel MOSFET on the high side, so the drain is connected to 3.3 volt and the source is connected to the load and the load is also connected to the ground, then we can use the GPIO pin with 0 volt and the N-channel MOSFET is switched off. But if we now use the high state on the GPIO pin, we see that the N-channel MOSFET is not switched on. So if you use the N-channel MOSFET in this configuration, this is not working. And why is this so? As we may remember from the start, the N-channel MOSFET needs a positive gate source threshold to switch on. And if we look at our circuit and compute the gate source threshold, then we have 3.3 volt on the drain to source and also 3.3 volt on the gate. So the difference between gate source is 0 volt. So this is below the gate source threshold voltage. So the MOSFET, N-channel MOSFET, is not switched on. And this is just the way the N-channel MOSFET works. But if we now use an P-channel MOSFET and connect the source to the 3.3 volt and the drain to the load and the gate to the GPIO pin, now we can see if we switch the gate to 3.3 volt, the P-channel MOSFET is switched off. And if we switch the gate to 0 volt, the P-channel MOSFET is switched on and the current can flow through the load. If we now use the N-channel MOSFET on the low side with higher voltages, everything stays the same. We have our drain connected to the load and the source connected to the ground, and use the GPIO pin with 3.3 volt, and the current is flow from the voltage source through the load, if the load is okay with the higher voltage. Now if we look at the P-channel MOSFET on the high side with 12 volt, if we put 0 volt at the GPIO pin, the P-channel MOSFET switches on and the current can flow through the load. But now if we switch the GPIO pin high, the P-channel stays on, and we have to figure out why this is so. So we again look at the gate source threshold voltage and calculate the voltage at our 3.3 volt GPIO pin at the gate. And now if we calculate 3.3 volt minus 12 volt, then we get a voltage of minus 8.7 volts, and this is certainly above the gate source voltage that we need to switch off our P-channel MOSFET. So it's certainly clear that the P-channel MOSFET stays on and we have to consider another circuit. One solution for this problem is to use an pull-up resistor and also an N-channel MOSFET to switch the pull-up to ground. And if we now look at the state of our circuit, if we switch the GPIO pin to 0 volt, the N-channel MOSFET is switched off, and so the gate of the P-channel MOSFET is pulled to 12 volt. And if we calculate now the gate source voltage, we use 12 volt minus 12 volt and we get a gate voltage of 0 volt. So our P-channel MOSFET is also switched off. And if we now switch the GPIO pin to 3.3 volt, our N-channel MOSFET conducts and pull the gate of the P-channel MOSFET to ground, and the P-channel MOSFET is switched on and the current can flow through our load. And the same if we now again switch our GPIO pin to low, our P-channel MOSFET is switched off and everything works fine. So now let's raise in our example the voltage from 12 volt to 36 volt maybe, and we do the same. We switch the GPIO pin to 0 volt and our P-channel MOSFET is off. And if we now switch the GPIO pin to 3.3 volt, our N-channel MOSFET switches on and pulled the gate to ground, and now our P-channel MOSFET is destroyed. So why is is this so? We have to consider the data sheet and look at the gate source voltage. And if we calculate the gate source voltage, we get 0 volt minus 36 volt. So we get a gate source voltage from about minus 36 volt. And most of the MOSFET have an maybe gate source voltage level maximum from about 12 volt. So in our previous example this will work, but in this example we certainly destroy our MOSFET and we have to consider another circuit. So in this solution we introduce also an Zener diode to limit the voltage about the source and the gate of the p-channel MOSFET, and we introduce another limiting resistor between the gate and the N-channel MOSFET, so the flowing current between the Zener diode and the ground is limited to a certain amount. And we have to look at the data sheet what the limits of our Zener diode that we choose is rated. So if we now switch our GPIO pin to 0 volt, the N-channel MOSFET is off and also our P-channel MOSFET is off. And if we now switch the GPIO pin to high or 3.3 volt, the N-channel MOSFET is switched on, the current can flow between the gate and ground, and our P-channel MOSFET is also switched on. And if we now calculate the gate source voltage, the gate source voltage is limited by the Zener diode. So in our case, if we use a 10 volt Zener diode, the gate source voltage is limited to 10 volts and the current is roughly calculated by 36 volt minus 10 volt and we get 26 volt, and 26 volt divided by the limiting resistor is the Zener current roughly. And if we want to be precise, we have to take account that our pull-up resistor and our limiting resistor acts like a voltage divider, and also we have to take account that our N-channel MOSFET have also an internal on resistance. So this is the circuit on the bench. We have our P-channel MOSFET, the Zener diode and the pull-up resistor, and also here we see the limiting resistor and the N-channel MOSFET. And as a higher load, I use these 3 LEDs, 10 volt, 1 watt LEDs in series. And as you see, they are all soldered in series. So the plus and the minus are soldered together. And as a demonstration, I write a small script for the ESP32 and use the pulse width modulation, and I start with a pulse width duty cycle of 100%, so we see a flat line. And as I press the button, I lower the pulse width modulation to about 75%, then 50%, then 25%, then 12.5%, and so on. So let's change the timeline from our oscilloscope to have a closer look to our small pulse that we now get with our pulse width modulation, and we can see the relationship between our pulse on the GPIO pin and also the switching line on the P-channel MOSFET. So this is a closer look to the oscilloscope, and now we see the 100% duty cycle again. And now let's switch to 75% and we can have a look at the Vmax, the blue line from the P-channel MOSFET at around about 30 volt, and the yellow line is the GPIO pin at the ESP32 at a level around 3.6 volt. So now let's lower the duty cycle of our GPIO pin and we can compare the different lines of our P-channel switching. And below a certain level we see that our switching off of our P-channel MOSFET don't really follow our GPIO pin, and it even gets worse if we lower the duty cycle again. So I switch on the cursors of the oscilloscope and measure what's the difference between the on pulse and also the off pulse of the P-channel MOSFET and also of our GPIO pin. So this circuit is not able maybe switching more than 1 kHz, or as you see 1.5 kHz maybe is the maximum. But this really depends on the usage of our resistors. So every resistor and the internal capacitor of the N-channel on P-channel MOSFETs are building an RC circuit, and this is what we see here. So the charging and discharging of the MOSFET gates are limiting the frequency of the switching. And now some thermal consideration if you use one of the MOSFETs, and I use as an example this IRFU9024, and it comes with an IPAC package. And maybe if we want to use this at 2 ampere, we look at the data sheet for the RDS on, maybe at some ratings, and we see that the maximum on resistance is about 0.28 ohms, and we can calculate a power dissipation from 2 amps squared times 0.28 ohms, and we get a value of about 1.12 watts, and this is below the maximum ratings. And then we also need the R theta junction to ambient thermal resistance, and we get some values in air, one about 110 degrees per watt, and in PCB mount we get a value of about 50 degrees per watt. So we can calculate the maximum junction power dissipation in air and on PCB mount, and this calculates by the maximum temperature we have at the junction from about 150 degrees Celsius minus the ambient temperature of about 25 degrees Celsius divided by R theta, our 110 degrees C per watt. So we get a value of about maximum without a heat sink from 1.136 watts in air and 2.5 watts on PCB mount. So on conclusion we can say in air we roughly need a heat sink, and if we mount this on a PCB we don't need a heat sink. And another example with another P-channel MOSFET in a SOT23 package, and also we want to use this at 2 ampere, and this has a rating RDS on from about 120 milliohms or 0.12 ohms, and we have a thermal resistance junction to ambient R theta from about 83 degrees C per watts, and a maximum power from about 1.5 watt. That's calculated by our maximum junction temperature 150 degrees C minus 25 degrees C divided by 83 degrees C per watts, or we can also see this value in the data sheet. So we have only power dissipations from our 2 amperes from about 0.48 watts, and this is way below our 1.5 watt maximum without a heatsink. So we can conclude that we can use this P-channel MOSFETs without a heatsink. So thanks for watching and clicking my video. I hope you find this useful or even learn something today, and maybe you give me a thumbs up or subscribe to my channel. Thanks for watching. I wish you a nice day. See you next time, and bye bye.